We are back once again. It is day 16, 17, 18, 19. We will never know. But another day, another day, another dollop of gratitude actually for the grind. So, we're back once again. We have 2 problems on the board. I'm a little strapped for time, so we're going to do a classic 20-minute banger, and then there's no compromises, so it is what it is. I'm going to jump into it. Apologies for the video yesterday. The recording system just got trashed somehow. OBS just be like that sometimes, and honestly, we just be like that sometimes. Humans just be like that sometimes. So it is what it is. We're just going to jump into it. So we have linked list cycle and convert sorted array to binary search tree. So I'm just going to jump into it. You can't see the 20 minutes because I'm trying something a little different this time, but I'll try and add another 20-minute timer another time. So let's just go. So we have linked list cycle. Our goal is linear time with constant space. So let's just jump into that. This is the binary tree in order from yesterday. Let me close that real quick. So we have a linked list cycle. Function has cycle, right? We have a list node, right? And we have a Boolean that we're supposed to return. It seems like we're going to be given a linked list, right? And we have to determine if the linked list has a cycle in it. So you can do this with Floyd's cycle finding algorithm. No need, I don't feel a great need to read the problem because it's just determine if the linked list has a cycle in it. And so the way that works is you're going to have a fast node and a slow node, which will be named turtle and rabbit respectively. And turtle is going to start one node in front of rabbit because we're going to have a while loop that is determined, right, determinate on them not being the same node, right? So while rabbit does not equal turtle, right, we're going to say rabbit equals rabbit.next. Rabbit equals rabbit.next and turtle equals turtle.next, right? And in here we're going to check if so they're both running. We're going to go to the linked list, right? Rabbit's going to move twice as fast as turtle, and if they get into the cycle, they should eventually meet each other, right? However, if rabbit ever reaches null, right? If rabbit ever equals null, right, we're going to return false. There is no cycle. And we know there's no cycle because rabbit moves twice as fast as turtle. So if rabbit reaches the end of the finish line, right, then we know there's no cycle. Outside of here, right, we're going to return true, right, because to exit this while loop, rabbit must not equal turtle. And if they are equal to each other, then that would mean that it's a cycle because they found each other. So I'll run it really fast with 3 and 2. So rabbit equals head, right? So we're already wrong. We want turtle to equal head and rabbit to equal head.next, right? So turtle's going to start at 3, rabbit's going to start at 2. While rabbit does not equal turtle, they're not the same. And rabbit is not null, so we're going to go rabbit next.next. It's going to go 0 all the way up to 4, and turtle's going to go to 2. Rabbit's not null, so rabbit's going to go twice, so from 2 to 0, right? And then turtle's next iteration is going to equal to 0, right? On that next iteration, we're going to go back to the top and check if they're the same. They will be, so we'll return true. And in the case where head is null, I was just going to mention that we should handle this case, and then I forgot to. One of the problems with going too fast. Oh, and it's not if rabbit is null, it's if rabbit's next step, right? Because we're going .next.next, so we know we can go .next.next if .next is good. Problems with going too fast. Being strapped for time. Oh my god. Okay, if rabbit.next say if rabbit is null. Yeah, I'm literally just speed running by guessing, by forcing submit. So I'm gonna stop and just think for a second. So if rabbit does not equal turtle, they won't equal. If rabbit equals, or was I failing out with 1, 2? So turtle equals 1, rabbit equals 2. Rabbit is not null, so we're going to dot next, but you can't go dot next twice. So we want to say if rabbit is null, so if rabbit's current position is null, or rabbit dot next equals null, then we want to return false. So I feel good about this one. There we go. So we're just going too fast. And it's funny because both times I swapped it, I ended up, it was just both of these if cases. So I removed this one for this one, and we still failed. I removed this one for this one, and we still failed. So in the end, the goal was just that we needed to just take it slower and just put both in. That's why it's always important to go line by line and make sure your assumptions make sense. In this case, they didn't make sense, but we got caught by some edge cases, 2 to be exact. So I'll make a note, and it's, yeah. So that looks good. And then we have convert sorted array to binary search tree. I clicked the image by mistake. Let's click problem. So we have a sorted array, right, which is an array of numbers, and then we have a tree node. So given an integer array nums, where the elements are sorted in ascending order, converted to a height balanced binary search tree. Height balanced binary tree is a binary tree in which the depth of the 2 subtrees of every node never differs by more than 1. So we're just converting a sorted array to a binary search tree, but since the array is already sorted, we just technically have to convert the array into a binary search tree. And since that's the case, sorted array to a binary search tree. I see, sorted array to binary search tree. This one is one that I'm realizing I need to take more time with. So we have this sorted array, and we want to convert it to a binary search tree. A binary search tree is where for every node, the left node is smaller than the middle node, and the right node is greater than the middle node. So it has to be true for all of them. So -10 is less than 0, and -3 is greater than -10, 9 is greater than 5, but 5 is greater than 0. So how can we convert this to a tree node? Well, we could do a binary search over the array. I mean, we could just do a binary search over the array, but how does that translate into a tree node? How does that translate into a binary search tree? That's the case. What we really need is just an in-order traversal, right, of this. So if we, in a way, we could view the array of numbers as a binary search tree, but in array form. If we do that, maybe we can just convert it to a binary tree based off binary search tree based off how you would but the height balance requirement just means we would select the center of the array on each pivot. So that is very interesting. That is very interesting. Binary search tree. So if we were to perform a binary search, but recursively, a recursive binary search, then we could probably create VST So maybe that would start with something like, you would choose the range of 0 going to nums.length minus 1, so that'd be -10, -3, so that'd be 5 elements going to 5. We'd calculate our pivot, which would be index 1, right? So that would be our center. And then from here, we just want to maybe, if we calculate our pivot, from there we would create a node. If we create a node there, we would have our center piece, which would be 0. Now we need to place -10 and -3, but it depends, because in order traversal is not a unique solution for this. There's multiple answers. If you have the range 0 going to 5, we have the range 0 going to 5. We have the range 0 going to 5. Calculate our pivot, which would be index 1, which would be 0. From here, to do an L, well, we could create a tree node with the value for the current node, and then we could just go left. So I think we could actually do this with helper. We'll start from 0 and go to nums.length, and we should probably handle if the array is empty. So we'll just say if nums.length equals 0, we'll just return null. Otherwise, we want to return helper going from 0 to nums.length. This is going to return a node, so helper is going to take left, which is going to be the left range, and right, which is going to be the right range, and return a tree node or null, right? So if we do if left is less than or equal to right, outside of that we want to return null. Why is that? Right, because when we go outside of our range, right, it means we don't have an actual value that we can calculate. If right is less than left, we'd have -1 and 0. We actually can't calculate a usable pivot from that. So we'd have right, which is -1 minus 0, which is -1 over 2, which is -0.5, plus left, which is 0. So we can't index an array with a negative value, so that doesn't make sense. All right, so in that case, we know we don't have a valid value in the array, and that also means we're going to need to pass in nums, right, so that we can actually access what we're aiming for. We have to change nums.length to nums.length minus 1, right, because nums.length is exclusive of the well, basically the last element in an array is num.length minus 1. So now we're in here and we want to calculate our midpoint, and that's typically done with left plus math.floor. The math.floor is specific to JavaScript because we can't enforce integers. We do right minus left over 2 semicolon, which would give us our midpoint. Then from here we could create a node, right? So we'll create a new tree node. This tree node will get the value of nums sub mid, and so now we'll have 0, right, which is the center, and we want to go left now, so we can do that, right, just by recursing left by calling helper again. So we can just say node.left is going to be equal to helper, but the new range going from 0 to pivot minus 1. Then we can do node.right is going to go from pivot plus 1, right, going to right, and then we can return the node. We have to return the node because we're setting helper, we're returning helper here. We're also, when we call helper, it returns a node, right? So it must pan out. And so what we're really doing here is if we call this with -10, -3, 0, 5, and 9, we're going to pass in 0 and 5. 0 is less than 5. Our midpoint is going to be 5 minus 0, which is 0 over 2 is 2.5. Floor is 2 minus left, which is 0, is 2, which means our center pivot is going to be 0. We're going to create a new tree node with a number sub mid, which is going to be this number 0 here. and we're going to recurse left. So in our heads, we can push a new function call with 0 going to pivot minus 1, which is going to be 0 and 1 onto this stack. And so we have 0 and 5, and now we have 1 and 0 and 1. And so 0 is less than 1, and then 1 minus left is 1 over 2 is 0.5. Floor to 0 plus 0 is 0. And then we have neutrino. We're going to create a neutrino node with num sub mid, which is 0. And the 0th element is -10. So it looks like we're actually going to be creating this one. So we're going to place -10 for our new node, right? Nothing's connected yet. And then node.left is going to go from 0 to pivot minus 1, which is going to be 0. So we're going to push that onto the stack. So now we have 0, 0. Since we have 0, 0, they're both equal to each other. But so we're going to go in, but the midpoint is going to be 0. No, our pivot is actually 0, so 0 minus 1 would be -1, which would mean that when we get into left is less than or equal to right, we actually wouldn't go in here, we'd return null. So once we return null, we'd have -10, our left hand side would be null, right? And so we pop that off the stack, the 0, -1, and then we go to 0, back to 0 and 1, right? And we're going to call right now with our pivot, which was 1. Our pivot, which was 0. Our pivot was 1. And our pivot was 0, so 0 plus 1 is 1. And our right, which is 1. So now 1 equals 1, right? They cancel out over 2, 0 plus 1. So now we're going to choose index 1. We're going to create a node, right? With num submit, and num submit is actually going to be index 1, which is going to be number -3. Once we have -3, we're going to create it as a node. We're going to do helper for both of these functions for left and right, but they're both going to return null because pivot minus 1 would be 0 and 1 is not less than 0. Pivot plus 1 would be 2 and 2 is not less than 0. 2 is not less than 1. So we just return the node as is. We'd pop that off the stack, and so now -10 would be connected to -3, right? We'd pop that off the stack, and then we'd be at 10. Pop that off the stack, and now we're back to our original call with 0 and 5, except now we set it equal to node.left, and now we can do node.right. And so I think this is fine. Okay, it's not fine. We neglected to call nums. So by checking the logic, I ended up actually not checking the actual code. Okay, I'm going too fast again, I guess. Comma is expected, and I wrote a semicolon here. I wrote a semicolon here for some reason. On line 19, the comma is expected. I'm not sure why. And I used pivot even though I'm calling it. Oh boy, mixing names. So I'm actually, maybe going forward, I'm going to write pseudocode solutions first. And I said 0 for this. This should be left. Now I'm noticing it's really, I mean, what they say is it's not about how you practice, it's not about what you practice or how long you practice, it's about how you practice. So I think when I'm strapped for time, or I think I'm going to, I just need to maybe do it first thing earlier in the day so I can take my time. Because rushing like this is going to have negative effects later on, so I need to be cognizant of that. If I train like this, then it's not going to have actually good outcomes later on. But what I'm thinking now is that the way this actually works is just recursion, but we're using the pivot portion to actually help us calculate, or the pivot map to calculate what node we should use. And the reason this is useful is because it can handle when left and right, where the range is odd or even, right? So we default to, if we have 3 nodes, we'll choose the second node in the middle. If there's 2, we'll choose one on the left. Well, why does this work? If we take out, we're recursing basically with L and R, but the implementation looks a lot closer to pre-order. So this honestly looks like pre-order. So pre-order, I'm trying to turn this function into a system that maybe could be abstracted for use in other systems, but I'm not seeing exactly why. I mean, I understand why it worked, but I'm not seeing the system behind it. So if left is less than right, what does that mean? It means, I know what it means, but I'm just not seeing the system. I think I need to take a closer look at this problem or engineer a algorithm that aligns more closely with how my brain works. This is supposedly an easy, but it could also mean that I just need more practice with tree-like problems to get it in my head. But I would say that's a wrap. We got it right. We went too fast. I'm going to be thinking about this one for a while. There's something here that I'm not exactly understanding. But that looks good. I appreciate the gang for tuning in. Make sure to join the hyperbolic coding chamber. We have thousands of people now. They're learning how to program, and they're okay, this is cap. There's only me in there. There's 2 people in there, but there's a lot of work being done. So if you'd like to join, feel free to join. And yes, we'll do a longer session tomorrow, hopefully.